Okay, so good afternoon, everyone. This is the fifth day, or fifth in the series, so the second last. So hopefully we will go deeper into quantum. But I just want to say one thing because I realized I said something a little bit incorrect last time. I'm sure that correct or incorrect, I'm not sure how much it's impacting, but nevertheless, I think for the record, since it's being recorded and so on, it has to do with the cat map. So maybe just to remind you, no, actually I should, it's in a separate. No, I'm not recalling everything, just this particular cat map. I just want to point out one thing, that it was a map on a torus onto itself. So A, B, C, D are integers, and QP gives you Q prime P prime. Now, if this is linear map, then of course there's no chaos in it, but there will be instability if, first of all, this is area preserving. We require that AD minus BC is 1. And so the eigenvalues of this depend only on the trace, A plus D. And if this trace is larger than 2, then it is unstable. Because everywhere the eigenvalues of this, one is positive, one is larger than 1, another is less than 1. So there is an expanding and contracting direction. And therefore, this is an unstable situation. You can think about it like an inverted harmonic oscillator. However, we can make this into a chaotic system by wrapping this around in this torus. So there is a modulo 1 condition on both Q and P, and so there is this Q and P, and it's going from 0, 1 to 0, 1. So now it's unstable, so things are being pulled apart like that, but it's also being pushed inside because of the modulo 1 condition. So there's a stretching and a folding that's going on. And if you repeatedly do it, it's a completely chaotic system. And the Arnold cat map is a particular realization of this. And all the cat map, the families of these, they are technically automorphisms of the torus, are when A, B, C, D are integers. So A, B, C, D are integers. So in which case, this is actually a continuous and in fact a differentiable map on the torus onto itself, despite this modulo 1 condition. And we showed this picture of what happens to Rajnikant when it's being iterated, comes back after some time, and that time is coming because of the following reason, which is where there was a slight miscommunication. So let's take the particular case of the Arnold cat map, 1, 1, 1, 2. This to the power of any time n, Q0, P0, modulo 1 is Qn, Pn. Okay, so, but because these are integers, it leaves an integer, it leaves a rational grid invariant. So you take an n by n grid, a rational grid, let's say, so you will have 0, 1 by n, 2 by n, etc. So it leaves such a square grid invariant because these things are integers. So that's why when you took that picture or any picture, which is a 256 by 256 array like this, which are sitting on this, they are like a rational array, and therefore there is a repetition which is coming at a time when this 1, 1, 1, 2 raised to the power of capital N, or let's say some period t, which is a function of this n, modulo n is equal to the identity matrix. Yeah, I think last time I said modulo 1. Of course, this is all integers. So you take modulo 1, everything is 0. Okay. So this n here is this n by n grid. So the larger, the finer the grid is, the longer this time is at which this recurrence is going to happen. For those grids, it's 256, in which case this T of n is 196. So it's quite a complicated function how T of n behaves as a function of n. It's a number theoretic thing. And those of you who are interested to follow up, it's an article by Dyson and Falk in American Mathematical Monthly. Around 1990, I'm not sure of the exact date, but you can always go. Because when you are acting on this rational grid, so either you can take these to be fractions, and then there is a modulo 1, or you can take these to be integers, and then there is a modulo n, which is acting on this. So, so that's the idea. So in fact, by the way, I should say, yeah, so in the rational grid, they are all like some m by n, n by n. Yeah, mn are going from 0 to n minus 1. So in fact, it looks pretty much like the quantization of the torus. This was quantized in 1980 by Berry and Hane using optical analogy. And not just this cat map, but a family of cat maps, and there's a whole literature on that. But what is interesting is that in the quantum case, this capital N is precisely the role which I mentioned about capital N there of an inverse Planck constant. And so this n going to infinity is a classical limit. And this period is also a quantum period. So this looks like a classical period because of this. Turns out that actually the quantization, it's like a harmonic oscillator. There's so much quantum classical correspondence despite the fact that there is chaos. It's linear and it's actually quadratic. If you were to write the action, it's quadratic. It turns out that this is exactly the quantum period as well. So there's a whole host of quantum cat maps that I'm not going to discuss. And there's a lot of analytical results available for this cat map. Okay, so that's something. The other one which I talked about was the quantization of the standard map, and which is a whole family of Floquet systems, Floquet time periodic systems, in which you can write down the Floquet operator explicitly in this form as a product of two exponentials. And so this is a general form, and there are two phases which are coming in here, alpha and beta, which you can use to make or break symmetries. Importantly, beta is used to break time reversal symmetry, alpha to break some spatial symmetries like parity and so on. So this is a whole host of things, and here this capital N is the is quantization on a torus, and this capital N is actually equal to 1 over h. Now you might, h is something which is dimensionful, so 1 over h being n, the 1 in the numerator is the area of the phase space. Okay, so unit area we have taken. So if you have taken some other area, it's basically the area of the phase space which has the units of action divided by h, which would be the number of supported states in that. Okay, so in particular for the standard map, where there is a kinetic energy which is quadratic and potential which is a cosine, with these phases being 0, both these phases being 0, there's a very simple form of this. There's no sum. The sum can be done exactly rather. And it's quadratic in this, so that's coming from the kinetic energy part, that's coming from the potential energy. There's one parameter k, the other parameter is n, which is the inverse Planck constant. And this is the dimension of the matrix n by n, and this is an exact unitary matrix which can be studied for quantum classical correspondence in a very simple way. And this should Yeah. Okay. So let me also point out to another quantum Baker's map, which we have studied, the Baker's map, which is the 2D area preserving version of the doubling map, exactly solvable and so on. In the standard map is quite a complicated scenario, and we know some aspects of it, but not exact solvability. We know some fixed points, low order fixed points, period 2, period 1, and so on. But if you were asked to find out all the periodic points of k equal to 10, let's say up to period 10, we know that there will be a very large number, but it's difficult to find these. Whereas in the case of the Baker's map, everything is given to us on a platter, it's solvable. It's a bit like the cat map, except that it's even more solvable, it's even more simpler in some sense. And recall that that's what's happening, but actually let us motivate the construction of the Baker's map, quantum Baker's map, by first taking this simple canonical transformation. By the way, when I'm saying map, area preserving map in 2D or in even higher dimension, you can just think about it as, we have already come across this as canonical transformations. Every canonical transformation is a map because it's taking you from one set of Q and P to another set of Q and P, and it's a discrete transformation. And in fact, all the maps that we are considering as dynamics have to be canonical because dynamics is a canonical transformation. So you may think about this simple canonical transformation where QP goes to 2QP by 2, clearly area preserving, and area preserving, therefore symplectic, etc. How do you quantize this? Suppose you were given this. We are usually used to quantizing Hamiltonians. You're given a Hamiltonian, you replace Q by this operator, P by minus I, D by dx, etc. But if you're given just this transformation, how does one construct a quantum operator out of this? So this is a discrete operator. So suppose you're given a canonical transformation rather than a Hamiltonian. How do you quantize that canonic? What is the corresponding quantum object? So the construction goes by, actually goes back to Dirac, is starting from a generating function. So generating functions, remember again, causes and classical mechanics, any canonical transformation or symplectic transformation has some generating function, and there are 4 types of generating functions depending on the kind of transformation. One of them may be natural. It turns out that in this case, the natural generating function is this F2 type according to Goldstein. The F1 is involving old position and old and new positions. This is a mixed type, old position and new momentum. Very simple. So 2Q, the new momentum, old position, new momentum. And the generating from this generating function, you can get these conjugate pairs by taking derivatives. And you see that if you take derivative with respect to small p, you get 2p. And therefore, this new momentum is the old momentum divided by 2, which is precisely what you want in this canonical transform. And the other half of it is new position, derivative with respect to the new momentum. And that is 2q, which is also exactly what you want. So this simple generating function works. Once you have a generating function, how do you associate a quantum object to it is coming from this correspondence that the exponential... That is coming from generating function. So suppose you have a generating function of type 2, you can, so it's any function of old position and new momentum, you can generate a canonical transformation with this prescription. It's the known thing from generating functions. So you have, like action itself is generating function. So you can generate yeah, this is action. This is one of these actions, yeah. Strictly speaking, a generating function. An action is a special case of a generating function. Yeah, I mean, so if you're so I mean, it's quite simple. Like we say that momentum generates positions, right? So that's because of precisely this. You can use momentum and then use this, so the new momentum as the generating function, then you will get a translation in position. And similarly, that is actually starting from identity. Identity is generated by Q times P. Q times P generates identity. In fact, the quantization, or Q times Q, sorry, Q times capital Q generates for you identity, or even Q times P, I guess. Yeah, Q times P generates identity. And so this is, so momentum generates translations in position, position generates translations in momentum, Hamiltonian generates time evolution, all that. Those are infinitesimal generators. Angular momentum generates rotation, similar, same things. And in fact, time evolution, because evolution is generated by the Hamiltonian, the exponential of the Hamiltonian gives you the quantum propagator. It's exactly the same thing. And so you would exponentiate this generating function. And now again, because it is actually connecting positions and momentum, so the quantum object is in this old, if you think about this as an old position and to new momentum, so this is an mixed representation. This operator is written in position, momentum, mixed representation. It's not a pure momentum or a pure position representation, is given by this exponentiation. If your generating function was of the first kind, Q, capital Q, then you will get pure position. But you can't write down a generating function for this transformation in that way. So you need to go through this.
So, Arul, you are saying like given any classical map, you can create, you can find this quantum map.
Generating function and exponentiate it to get.
So, for example, in the previous case, this U, which is your map.
You can get it in the same way.
But that was already you got in quantum, but if you have in classical description, you are saying also can be.
Absolutely. In fact, when you are doing semi-classics, that is very useful. So for all the class of standard map and so on, we can write down an action principle, all of that. And that action will be the generating function of this transformation. There, in fact, the first type generating function can be written down, meaning new position, old position. And the quantization will then follow. Here for the Baker's map, the natural thing is this mixed representation. And therefore this, if you put here, you will get 2qp divided by h bar. Remember that qp divided by h bar is the Fourier transform. So this 2qp divided by h bar is like as if h bar is divided by 2. That kind of a Fourier transform. Okay, so, and this 2, remember, is coming from the Baker's map or doubling map 2. And so, to cut down some more story, I mean, you can see there are many versions of this quantization. This goes back to the late 80s, and Balazs and Voros first said that, therefore, you can use such an approach to write down a quantum map, again on a torus, so it's finite, so h is replaced by 1 over n, as this Fourier transforms gn by 2, which is actually coming precisely from this 2, and that is n by 2. And this gn by 2, this is coming from 1/2 of the Baker's map, remember, takes you like this. And there's another half that is coming from this gn by 2. And then this whole thing will be in a mixed representation. So you can go to a pure position representation by doing a full inverse transformation, inverse Fourier transform. So at the end of the day, this, suppose I say that, suppose we have quantized this Baker's map, on the torus, and we know that it's fully chaotic and so on, the quantum Baker's map is a very simple object consisting of Fourier transforms. And we know the Fourier transforms can be very efficiently implemented and so on. And therefore, this is a simple object which seems to be quantizing one of the most chaotic systems if abstract. And this Fourier transform, Saracino pointed out that if you include anti-periodic boundary conditions, as I said, there's alpha and beta, there are 2 boundary conditions. If you introduce anti-periodic boundary conditions, it kind of maximally preserves classical symmetries. And so this is a nice transformation.
So, Arul,
yeah.
Q and P, can I think of those as operators?
Where? Here?
No, when you say that Q goes to Q and P goes to Q and P.
No, I'm thinking of purely classical. This is all purely classical. This is all purely classical. Even here, they are only numbers. See, it's coming as a representation of this operator.
But then what is U is an operator?
U is the operator. U is the operator. U is the operator. See, the entire, in fact, path integral formalism of Feynman was based on this comment from Dirac's book. And so the propagator is just exponentiation of the action. So the action there is classical action over a short time, and then you build the whole thing in a finite, for a finite time from infinitesimal generating functions, actions. So yeah, so this is in that spirit. So it's purely classical.
I'm just trying to understand what does the map Q by to 2Q P by 2 mean in the quantum context?
You and P are not well defined in quantum.
Yeah, so what it means is if you act on, roughly speaking, what it means is if you were to take a position eigenstate n, act on this B, it should go to 2n. Does it? It will go, if you use this map, you will see that in the large n limit, it goes to 2n if n is smaller than n by 2, capital N by 2. That is this 1/2, and so this modulo 1. Okay, this is just the position representation, but it should be good enough to give you also what's happening in momentum. That's the thing with the quantum. And there is no quantization of the doubling map per se, but quantization of the Baker's map is there. It's coming from this. So there are many versions, I would say, of the Baker's map. After that, there's been a riches of Baker's map. I could talk a lot on that, but I will restrict myself, except to say that there's a book by brother of Penrose that we were discussing, Oliver Penrose, on statistical mechanics, quite an early book, before all this quantization was done, where he gives a problem, quantize the doubling map. So that's more like 0 point. Actually, I think he was just talking about the left shift map. Okay, and so let's say that you want to quantize this left shift map. His solution was actually something like this. It says, okay, now let's take a bunch of spin half particles of qubits or something like that. So you have a state of one of them. A state of, let's say, k minus 1 qubits. You write it like this in the product basis. And then you have some operator which gives you want to left shift this. So you want A1, A2, etc. You don't know what to do with A0. So he put it here. Okay, so this may seem like a quantization. You can pursue with this quantization, and you will see that this does not give you the Baker's map. It gives you something else, which is resembling the Baker's map, but it's not. And also you can see that immediately this is periodic with period k. So you may think about this as some, it's some approximate version, but this is not periodic. And so in fact, this has random matrix properties and so on. And for n, which is powers of 2, it has some interesting states which are multifractal. You can see maybe a bit of that I can show. Okay, so I just wanted to point out that there are these very simple finite unitary matrices which are quantized objects of these classical maps. In this case, there is no parameter, but it's quantizing a completely chaotic system in which you know all the things. Like, for example, you want to play around with some concept. You could use this. There is a lot of analytic things that can be done, although not fully solvable. Nobody has found the eigenvalues and eigenfunctions for a general n. And this is a model where you have a parameter, you have a more generic transformation, but not all classical features are known exactly analytically.
Originally, you had this quantum evolution operator for the kit.
Yeah, yeah.
So there you was getting this tau particular value while you have like ballistic drone.
Yes, that is for the thing on the cylinder.
Yeah.
Yeah,
Not like diffusive.
correct.
How do I see that in your map?
You want me to go back to that?
No,
Hmm.
there you explained, I can see.
Yeah.
That,
Such a thing does not happen here.
it does not happen.
No, no, no. In this case, there is no quantum resonance as such that's going on. Although there may be some special values of capital N for which you might have special things going on. Yeah, so otherwise these are pretty generic objects. There's not anything funny. There's not anything which is, of course the whole thing is quantum, but
Then what is the difference between quantum and classical map of, like you were showing us like Baker's
it's
map
the
of-
difference between quantum and classical of anything. Why should there be, see, a resonance is an extreme case where you don't have a classical equivalent at all. Yeah, but in these cases it's between classical and all that is.
So what I'm asking,
Ah.
what do you see the differences when you, like in classical Baker maps, you also have like maybe cavity bridging while you are showing.
We'll see, no? That's what the whole story is. The whole story is to compare classical and quantum. Yeah. Okay, good. So, all right, now how do we compare quantum and classical? And there are many ways of doing that. So one of the ways that I like, and which is visual therefore, and therefore it's nice, is to use coherent states. And this is not just me. I mean, everybody uses coherent states because they come closest to classical. Okay. So now we have been saying things about a torus topology for the phase space. Therefore, it'd be good to construct coherent states on the torus. So they are constructed using displacement operators on the torus. I've already told you about translation and position and momentum. So if we can find a ground state which is looking like some state which is highly localized, like a coherent state for a harmonic oscillator, ground state is a coherent state, minimum uncertainty state, and then you can translate that minimum uncertainty state to different position momentum, that will give you the collection of coherent states on the plane. So you do the same thing, except that it'll be good to have a Hamiltonian which respects all the torus boundary conditions. So here is this nice Hamiltonian. It's in fact Harper, we have already mentioned that. There's no kicking in this. So this is an integrable system. It's a flow on the torus. You can work out the phase space. And 2 minus cos q minus cos p. So let's just look at it very simply. Okay, let's look at these as classical functions, q and p as classical variables. Cos 2 pi q around q equal to 0 is 1 minus q squared by 2 and so on. This is also 1 minus p squared. And so that's why I put a 2 there. So it cancels the 1 on both of these things and it becomes q squared plus p squared, which is, is a harmonic oscillator. And in fact, that is therefore a stable fixed point. So this is around the origin, a stable fixed point, which is looking locally harmonic. And therefore, you can look at the you can do the quantization of this on the torus. That is, you can write down the this Harper Hamiltonian using all those bases which I mentioned. It will be an n by n matrix. And you can find the ground state of that, which will give you which will be a highly localized state at 0, 0, which we will use as our ground state or fiducial state as the jargon goes. And then this is going to be very much a minimum uncertainty state localized around here, and we will simply transport it. So to transport it to a different position in momentum not being 0, let's say n by n and m by n and m are integers between 0 and n minus 1, we just use our translation operators in position. By n we translate momentum by m. And then you will get a state which is localized at this point in position momentum, and it is going to be almost a minimum uncertainty state. So it's a well localized state at q0, p0. And then we can visualize anything using these bunch of states. So there are now n square coherent states. They are not an orthogonal basis, and even normal coherent states are not orthogonal. They are overcomplete, and this will be the kind of situations here. For example, if you have a state psi, which we want to visualize. It can be some time evolving state, eigenstate, and so on. We want to visualize. We will see how much of it is there in the coherent state Q0, P0. It will give you some idea of what is the localization at that phase space point. So this gives you some phase space picture. So you can take modulus square, the intensity of this overlap, and it's called the Husimi function. Okay, the Husimi function of Q0, P0. So it's a positive definite function which will tell you kind of, you can start from a state and you have a distribution on the torus. Yeah.
So if the translated state,
Yeah.
you are acting PQ first and then TQ.
Yeah.
But P and Q, they might not come.
They don't come here.
So if I, let's say, I
You can do, so you will get a family. Remember, there is a Weyl commutation relation, this one. So when you take those powers, if you are interchanging these, it will lead to a power.
just a phase.
Yeah, it will lead to a phase. Okay, so now how does this look? Let's take a coherent state localized at 0.25, 0.75. Here I've taken n to be 100, so this is at 25 and 75. You can read it as 0.25, 0.75. I haven't bothered to divide it. And then we take an overlap of this state. So this state I'm getting like this. Okay, I've diagonalized this, taken the ground state. I have translated this Q by 25, P by 75, and I've got a state. I want to visualize that state. I now take its overlap with all other coherent states. So it has no overlap anywhere else. It's pretty much zero everywhere else except at this point, right, where it itself is maximum. So this is visualizing. So this is as good as a point in phase space. And the width of this is going to be approximately 1 by root n, because the area of this is going to be 1 over n, which is h. So this delta q and delta p is approximately square root of h bar, is scaling as square root of h bar. So as n grows, h bar decreases. So this is n equals 200. You can see that it's more well localized. That's all. So that's why as n is increasing, you will be getting more and more classical.
These are all torus. That means I am supposed to think this periodic boundary condition in both sides.
Yeah,
right?
yeah. So if I actually plot 0, 0, which I haven't, but you will see later, it will be peaked here, 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 and here. Okay, good. So yeah, I think this I have already said. This is what we are going to do, and there are these periodic boundary conditions. So for example, we can time evolve a state. You're given an initial coherent state. Z0 includes Q and P. You can time evolve it like this, or using a Floquet operator like that. And then you want to find the probability of Z0 finding this initial coherent state at a different coherent state at a time t. So that you will just calculate this. Okay. So let's calculate this, but maybe before we, okay, I'm just giving you some idea. So this one is for n equals 100. We are starting from the fixed point state at the origin. Remember that the fixed point is a fixed point classically.
So this is still going on Becker's map.
No, 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 no. This is standard map.
So that U operator U.
This U is standard map. Okay.
So that also has 0, 0 fixed point.
Yes. Standard map has 0, 0 fixed point. We discussed that it's a 0, 0 fixed point which becomes unstable at k equal to 4. This is an important point because we'll keep coming back to it. Okay, there are two fixed points. One is unstable for any k positive at half 0, and one the origin is stable till k equal to 4. Okay, so in fact we will start this coherent state. You see that here now. Okay, this first concentrate on the first row. So this is the initial state, and it's concentrated at the fixed point at the origin, and this k here is 1. Okay, so k is 1. So it's kind of, it's not very small, it's not very large, but it is this stable. This point here is stable classically. This is all quantum. Now we are evolving this for 8 time steps. You see that nothing much is happening quantum mechanically.
So Arul, again Q and P in the axis or?
Yeah, okay. So Q in this, P in this. For me, always when I'm drawing a square, Q is horizontal, P is vertical. And this is my torus phase space. I'm not putting any
And since
points.
you have started with 0, 0, all corner I see.
Yeah, all corners. They will be, it's not as if it's a stationary state, it's not an eigenstate. It will be distorting a bit, but it's not moving out much. Okay, because it's stable, it's kind of there in this neighborhood. Now let's increase K. So this is K is 2, it's still stable. You can see that there is more distortion. Okay, K is 3, you can see that there is a region like this. And if you remember, I showed you a lot of phase space. Maybe we can go back to that. I think that these are like the islands, the shape of the islands. Okay, or it could be related to an inverse time evolution of the islands. But you should be seeing that because the region around this is becoming unstable. And this island is starting to decrease. This is K equal to 4 when this point has become unstable classically. So you can see that there is more density quantum mechanically coming out like this. But it's not as if it's a whole lot. At K equal to 5, it has lost its stability. You can see already now that the density is going out and it's starting to fill.
Arul, sorry.
Yeah,
I see the K is increased from
1 to 8.
yeah, 1 to 8. And what is this side? Is
Time.
Time also.
Yeah, time is, no. This is what I'm calculating. I'm starting from 0, 0. This time is going from 1 to 8 for every K, and every row is K, fixed K. And this is for K is 5, it has lost its stability. You can see that this has become unstable. You can see some directions, unstable directions, and you can see that it's now escaping out into the whole region. It seems to be now escaping. But classically also, that island is actually destroyed. There is a small thing there. We can go back to some of those classical simulations if you wish.
Time will match at which time this
Huh?
and but no, the time at which it becomes kind of unstable means that you see that over time your
Yeah, it's becoming faster and faster. You mean,
no the time at which okay, so maybe this question
yeah.
can I also define here some kind of time scale over which it will become spread over this
Yes.
space?
Yes. So I'll come to that.
Okay. So that time scale will match between classical quantum, that was the question.
We'll see. So yeah. So now at this point, this is K. K is this is 5, right? 6, 7, 8. Yeah. So that is 5, 6. You can see that already now. This is So you can see that even in the second time step, this has elongated so much that actually they are interfering with each other. You can see these patterns forming. That's interference effects happening at a very short time. And then 8 and so on, it's very unstable. And you can see that this is forming here. I don't know whether it's sensible for me to, or maybe I should just continue and then we will see. Because if I start doing that, I'll probably never end. So let's proceed and then we'll see whether we need some more intuition in that. So I just wanted to give you an idea of what's happening to an initial wave packet, which we can kind of visualize classically, which is undergoing this transformation. So let's look at okay. So this is what? Okay, this is for a longer time. Okay, so this is for a longer time. The same thing. N equals 100. Stable fixed point. You see that nothing much has happened. This is stable fixed point. K is equal to 1. Okay, this was K is equal to half. This is K equal to 1. This is just longer time scales, that's all. Okay, K is equal to 1, 2, nothing much happens. 4 is when it is losing its stability. This point is actually losing stability, and you can see this, but it's still pretty much localized. K equal to 6, you can see that it is now some unstable manifolds, this will actually be classical structures. You will see classical structures like this if you were to start from a density like this. Here you will almost see classical structures, but you can see that when these coherent structures are interfering, they are starting to interfere here, then quantum classical correspondence is essentially broken down, and these would be quite different from classical, and the quantum, nothing much changes. It looks like it's already, yeah. The color is, yeah, I should have put a barcode, but basically red is high, red is large, blue is small. Okay, so there may be recurrences back to this, like there are sometimes, we don't know how significant those recurrences are, okay, this we can't judge from this picture, but they will be small if at all they are there in this case. Okay, this is k equal to 8, this I think here is the unstable direction, it's become unstable, so this is the eigenvalue larger than one direction, it's becoming more vertical, and these will be called unstable manifolds. When they start intersecting, this will be quantum, so it's creating these interference patterns which are quite non-classical kind of things. So if we start from the unstable fixed point at the origin, so even for half 0.5, it's unstable. So what happens? This is at time 0, it's starting from here, time 1, 2, 3, etc. And again, you see, classically, this would be the unstable direction. That's why it's turning out here. It's in this direction, so it's in the unstable direction. It turns out then because of the total boundary condition, this reappears here and then continues to elongate, and that's looking like the separatrix. And of course, there's a full torus, so this is also coming, you know, this is same as this. So this is the entire torus which is showing up here. And then there will be interference effects when you're starting from this unstable point and the separatrix point. You can see that here there is an interference, it's coming back to this initial condition, and then it's delocalizing again. So there are studies about semi-classics of starting a wave packet on a separatrix, which is interesting. And so from the point of view of actually, this will be called squeezing, because it's squeezing along some particular direction. And squeezing is always aided by instability. And it's squeezing along the torus, along the separatrix or unstable manifold. Okay, so this is more of the same, I guess, with larger value of the k. So you can see very clearly these things. And when k is as large as 2, you can see that it's now kind of spread out or delocalized in a region. And why isn't it penetrating here? Why is it dark? This is all 0 here. 0 here. Why is it? There is a fixed, that's the origin. That's the fixed point, and it's not lost its stability. There is a stable island around it, so it's not penetrating this, okay? And that's why you're seeing that it's not penetrating that. And k equal to 4, that island has become small, but it's still there, okay?
But sorry, I do not understand. You had that even that fixed point at 0, 0 means this corner also, but it's mostly that this of diagonal corner region are extended, whatever regular or no, yeah, like for example 11 time.
Yeah.
So you see that
Here.
the like these of diagonals are extended
Here.
Yeah.
Yeah. Yeah, that will be the region of the island surrounding the stable fixed point.
But that's a 0, 0 fixed point.
Yeah.
Right? But
0, 0 fixed point is here, 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 here.
yeah, but why these sides are more extended?
It's because it's not symmetric. There is a reflection symmetry, but apart from that, are you saying there will be a reflection symmetry about the center? So this will be the same as this will be the same as that.
But this would be all same, right?
No. There is no symmetry of that kind. There's only symmetry of reflection around the center. So you would have seen that even in the earlier things. Okay, so k equal to 4, k equal to 6, that island is gone, so it's penetrating that. There could be other small islands, but essentially it's not there. This is the unstable direction of this point, it's extending. You would say essentially if you start from something classical like this, you will definitely see this. You may see something like this, you will see these lines, but not from here. So if there's any classical quantum correspondence, it will break down at this time. Afterwards, it's looking like random waves of some kind. Okay, so that's more of that. 8, it's fully chaotic. And this is what happens to a period 2 point. Remember that there is a period 2 point which is stable till k equal to 2. And so this point here comes classically to the center. And that's what's happening quantum mechanically. Start from here, it comes here, goes back, it's a period 2, comes back. But you see, it's of course not rigid, it's undergoing diffusion. And the shape of this coherent state is changing, it's getting squeezed and so on. And so as time goes by, there's going to be interference effects. You're seeing these structures, they are interference effects, and they can become significantly large. So especially for larger value of k, you can still see the period 2 that's going on, but it has lost its stability. Here is the point at k equal to 4, this has become unstable. So it's no more going into those two. But you can see that there are times at which it can come down to that center as well. So these could be highly, quantum effects, where there are these orbits which are reconstituting after some time. This will not be a classical situation. All of this will have implications to the quantum spectrum. That's why I'm giving you some kind of a pictorial history of what's happening to the wave packets, because we can find eigenstates based on time evolving states. So the eigenstates will be influenced by all of this kind of things. Okay, so 6, let me progress. So there's nothing much here. Okay, maybe this is an animation. So let's go back. This I think I showed you probably the first animation, which is starting from a bunch of, so what will be the classical? Classical, you should not start from one point. Always there should be a parity between classical quantum. We are starting from a coherent state as a bunch of initial conditions which has a width of h. So you should start classically also from a bunch of initial conditions, a density of points with that width of h. And here I'm starting at, I guess, this is, by the way, the simplest. So this is k equal to 0. So that's integrable point. I'm starting at the period 2. So you can see that it's going period 2 and then it's spreading out. Okay, so that's classical. Now what do you think will happen quantum? We have seen all these quantum pictures so far, but we have not seen k equal to 0, the integrable case. But what do you think will happen if we run the quantum model? It will follow the classical for some time, and then it will spread out, right? Like the classical. And then what? Let's see. Okay, so we'll start. Period 2, so it's doing this. Okay, it's spreading out. Now interference has started. Now there's it seems to be spreading out. It looks like it's classical, but you can see already that this is far from classical. Classical doesn't have lumps forming. This has 3 lump forming, 5, after some time, 2. Okay, so it's come back to I shouldn't say that but it's coming back. So this is a well-known phenomenon of quantum revivals, okay, which is happening at a much later time. So there are 2 time scales. There are these time scales at which
Revival means when it sees the Hilbert space dimension. Is that what you say?
yeah, in this case, it's not for everything, but for integrable systems, especially simple integrable systems where you're starting with some simple initial states and so on, you can have revivals, particle in a box, and these are non-classical phenomenon where interference is leading to a constructive interference where the initial state may be reconstructed or copies of it, the cat states kind of thing. They are there you can have multiple copies of it, which is forming because of interference, which is completely non-classical. So you were talking about classical quantum. There will be some correspondence time. Then there will be interference effects. And these interference effects can give rise to various things. It can give rise to something like this, which is a complete recurrence or fractional revivals. These are called fractional when you have, the single coherent state splitting into several other coherent states like these. So this is just the spectrum when k equal to 0, because it's a free rotor, is just n squared, which is just particle in a box spectrum. So this is well studied in a particle in a box. It was kind of missed probably in the early days, but in the 90s, people studied fractional revivals in a very big way. Okay, so now I want to point out to time scales, since this was also asked, and it's very important. At what time scale are these two pictures, first of all, differing from each other to begin with? So to begin with, this is looking still classical, and then there is an interference occurring because the wave packet is diffusing because of the nonlinearity. Harmonic oscillator, it does not diffuse, it just rigidly goes around. Here, because of the nonlinearity, it is diffusing, and then the snake's head is catching its tail, and there is interference effects. So this is purely a classical time scale at which quantum effects start, and that is called an Ehrenfest time scale. Sometimes it's basically referred to as an Ehrenfest time scale. And it was pointed out by Berry and Balash rather early on that the scaling of this Ehrenfest time scale is 1 over square root of h bar. This is all dimensionless h. So it scales as 1 over square root of h bar. So clearly in the classical limit, h bar tending towards 0, the scale Planck constant, this time goes to infinity, and you have infinite classical quantum correspondence, infinite time classical quantum correspondence. But in a system where h is not 0, there will be a time at which interference effects start and quantum correspondence, classical correspondence breaks down. So for our systems, h is going as 1 over n, therefore it's scaling as square root of n. So I have here n is 100, so roughly about 10 time scales, 10 time steps, the classical quantum I'll expect it to survive with each other. Afterwards, it will not talk.
So is there a way to understand why the scaling?
Yeah, I'll come to that. Very simple arguments. And then there is this revival time scale, which is a super quantum it's a purely quantum phenomenon. The density, classical density, won't do anything like that. That occurs at a much longer time scale. Here you see that it's 1 over h or n. I have to wait for 100 time scales, basically to see that it's coming back to where it started.
That's what I was also saying. If the
Yeah,
Hilbert space dimension-
yeah. This is the Hilbert space dimension for the revival. You're absolutely right, yeah. So but there's also another time called the Heisenberg time. We'll hopefully come to that next time, which need not be a revival. Revival is something special that happens mostly in integrable systems. Yeah.
Does this pattern keep on repeating indefinitely, or is it just twice?
It will come back to where it started.
And after that, it's not going to go back to.
No, it will. It's completely periodic.
So it will keep on repeating itself.
Exactly. Quantum mechanically, it's exactly this thing. So you see, a recurrence like that is not that unusual. Even a harmonic oscillator recurs, but this is more than a recurrence. It actually is a fractional revival. It splits into two. Imagine one lump splitting into two. Okay, so that's something which is it's been observed in things like a Rydberg atom. Excited states of Rydberg atoms show revivals and so on.
That time period has nothing to do with the Ehrenfest time, right?
No, the Ehrenfest time is much smaller. This is square root of n, that is n. Okay, this is going as that.
I guess the physical meaning is the Ehrenfest time until when the classical and quantum behavior are similar.
Similar. So basically interference effects. I would say that if you have any localized wave packet of the size of as minimum uncertainty states, under time evolution, when does it start to interfere with itself or with other states? Mostly with itself. We are just talking about single particle things here. Okay. Okay. What was that? maybe I have to wait till it goes. Is it? Ah. Okay, so this is fully chaotic case. I've gone off from 0 to fully chaotic.
Sorry, Arul, my question's answer would be like the RNPS time, which you said order of root n, will be same for classical and your this quantum one, right?
There is, well, this is a quantum time.
But classically also in your...
See, the RNFS time itself is by definition the difference between classical and quantum. So there's no pure quantum.
RNPS time is...
Yeah.
You were saying classical and quantum are similar, right?
Right.
Now.
Yeah.
But what about like seeing, this is k equal to 0, but k non-zero cases, seeing the chaotic behavior emergence, that also you call RNPS time? Or
Yeah, so that's what I'm showing here.
that also
I'm trying to
RNPS
show.
time?
It's still RNFS time. You will see that, you will see here, you can see for some time they are the same. But the time is much shorter. So did you guys see the, let's first see the classical.
Yes. Can we see from the beginning classical one?
Yeah. So let's start from here. Oops. So it's stretching along this direction. It's forming these U bands and then they are just becoming. This is a very short time scale. So let's look at the quantum starting from the beginning.
And time are same steps, both of them.
Yeah, same steps, 1, 2, 3. So you can see that it's a very short time, 1, 2, that's it. Interference is started and afterwards it's gone. So this time scale is going as log of 1 over h, unlike 1 over square root of h, divided by the Lyapunov exponent. So it's log n divided by lambda. So it's extremely short time scale compared to the Ehrenfest time scale for the integrable system, which was going as 1 over, which was going as square root of n. So if you have something like million or something, you have 1,000 for the integrable system, whereas you have only 6 for the chaotic situation. So the Ehrenfest time is much shorter for the chaotic situations, and that's understandable because what's happening to any localized state is exponentially it's growing in size, and therefore the self-interference occurs at a very different time scale. Lyapunov exponent. Yeah.
Sorry, Lyapunov exponent in classical one.
Classical Lyapunov.
Quantum one, what you will call that?
No, this is classical Lyapunov exponent.
But the RNPS time, that TEF also true for the quantum case or no?
This is quantum, yeah. See, again, Ehrenfest is only there for quantum to say that it has stopped bothering about classical. It's not anymore like the classical. Yeah, but the time scale is estimated as divided by lambda. So that means that the larger the Lyapunov exponent is, also you have shorter classical quantum correspondence. Again, it's very intuitive because starting from a wave packet, the Lyapunov exponent is determining how fast things are being stretched out. So if you want interference to occur faster, your lambda will be larger. And if lambda is larger, your interference times will be shorter, and therefore classical quantum correspondence will not be. Oh, by the way, I have an intermediate case. This is 2.5. So I'm starting from a period 2, and so you can see that, yeah, you can see the classical and, okay, 2 and 2.5 I have. So, yeah, you can see that for the 2 case, it's quite remarkable that for a very long time, it seems to be still, this quantum classical correspondence is happening because it has just lost stability. Whereas at 2.5, it has lost its stability, the period 2 point. So it's now spread all over the place, and there can be revivals. You can see these revivals. Yeah. No, there is a time at which it has lost its correspondence. There is, however large your k is, there is a short time till there is a correspondence. Yeah, yeah.
Will that kind of flow pattern give me a fractal line behavior?
Not necessarily fractal, it depends on the system. Typically, they are like random waves. I'll come to that. I'll come to the description of that. Yeah.
So if k equals 2,
Yeah.
is the access time like root 10?
Yeah, this would be something like that. It would be. I haven't looked very closely, but I'm guessing it would. Yeah. No. So there are very special systems where, I mean, also special wave packets which people have put and actually have seen revivals, even in chaotic systems. But they are highly designed. It's an interesting problem in quantum control because it's like, this is your initial state, final state. I want to go to that even in a chaotic system. Can I do that? So there are very interesting, there's some interesting work around that direction. But typically, no, there won't be any revivals.
But there will be Heisenberg time, which probably was.
Yeah, but even at the Heisenberg time, things have, it will just squish around like random waves. It's kind of thermalized at some level. Okay, why Ehrenfest time scale? Let's try to see how to derive that, at least the scaling. Okay, but by the way, these are all time scales. It's not as if they're something happening at that definite time. But these are all time scales, and the scaling is also there. And you can see these time scales, and there are many time scales, in different quantities differently. Okay, so let's try to argue out for integrable systems. We said that there are action angle variables. So we'll take one action and one angle pair. So each degree of freedom has an action angle pair like this, where action is constant and angle is evolving. I can take a flow or I can take a map. Here I've taken a map like this. So, okay, so omega is this rotational frequency. So what is happening is that we are taking a bunch of initial conditions which has a spread both in action and in the angle. Okay, when we are taking a bunch of initial conditions, it's not as if we are fixing the action alone. We are taking a bunch of, so there is a delta in and a delta theta n. And it just evolves like this. You can just take a differential of this, delta theta n plus 1, delta theta n plus this. So it's a derivative of the frequency with respect to the action delta in. And delta in plus 1 is same as delta in. Therefore, if you start with the initial spread in actions, nothing is going to happen to it. Delta is 0. So we can immediately solve this equation. So delta theta n is delta theta 0 plus n, that's the time, times omega prime I0, because In is same as I0. That's the central orbit. Delta I0, this action thing here. So now, as you can see that as time is increasing, this delta theta n is growing. So delta theta 0 is something very small. So let's ignore that in comparison to this. And what will be the critical point? Basically, you have a bunch of things which are evolving along the angles. You have started with some delta theta 0. If that spread in the angles is as large as 2 pi, that's the maximum. That's when the snake's head is going to swallow the tail. It has come back. Its delta theta has become as large as possible, that is namely 2 pi. So that critical time, let's call it n star. So delta theta n star is approximately 2 pi. What will be the time? So the time will be n star, which is 2 pi divided by this frequency derivative divided by this delta I0. Okay, now this is all classical. Now we argue that we are taking an initial quantum state, which is minimum uncertainty. And this is the delta I0, delta theta 0, which is the spread in the classical, that should match the quantum H. We are starting from that. And we are not starting from any squeeze state, so typically both of these will be scaling in the same way, delta theta 0 and delta I0. And therefore each of them is scaling as square root of h bar, and then you can see that n star is then scaling as 1 over h bar or square root of n. So it's a very simple derivation, and it is independent of the number of degrees of freedom, because each degree of freedom will be having a different omega I prime and so on. But as far as scaling of h bar is concerned, they will be the same. shown that's the simple argument for that. And actually the chaotic case is even simpler. Chaotic systems, for each degree of freedom, again, let's look at it like that. So delta Qn, and now there's no action angle variables, so let's look at some delta Q0, delta P0 kind of spread in the degree of freedom Qp. So delta Q0 is exponentially growing in time with something which is going to be like a Lyapunov exponent, okay? It's exponentially growing in time. And when is this delta Q, time at which this delta Q0 going to become as large as the phase space? So that, let's assume that that's of the order of 1. So this is of the order of 1. So delta Q0 is then, yeah. And what is delta Q0? Again, from this argument, delta Q0, delta P0 is going to be the same. Delta Q0 times delta P0 is h. So this is scaling as square root of h. So you put that in here, but because of this exponential growth, you get a log of 1 over h, which is going to be scaling as that, and you see the Lyapunov exponent coming out of this. So this kind of simple arguments, which are based on just semi-classical or even classical arguments, is what leads to these time scales. So, by the way, I mean, if you, there's some things which have been pointed out by people like, I think, Zurich, that if you say that the quantum mechanics is all that is, there is no decoherence or open system kind of things, the kind of time scales which we are talking about when you have chaotic systems is so short. So if you have some macroscopic object, and there are macroscopic objects which are known to be chaotic from astronomical data, certain satellites of large planets, they are tumbling in a chaotic manner with a well-defined Lyapunov exponent over observationally, that you can argue that actually by now quantum interference effect should have taken place because this is a very short time scale because it's chaotic. And therefore, well, there should be other things. It's an open system, there is decoherence, and that's the idea of that. Yeah, so
I
yeah.
have a question about this login.
Yeah.
Are you assuming anything about the system? Like, because I do not know your Arjun's time, how comparable to the Thouless time what we talk.
Yeah.
That can be very different depending on system properties. We get n square, we get n0, many different scaling.
Yeah.
So you are getting log n. Log n comes there for the mostly non-conservative systems. Like there is no.
Yeah, this is non, I would say that, look, this is assuming that there is classical chaos. We are looking at classical quantum correspondence breaking down, okay? And and this is also, as you can see, these are arguments which are giving you some time scales. There can be a lot of subtlety which is underlying this. For instance, this Lyapunov exponent, lambda, it is, if you remember my definition of Lyapunov exponent, it had to do with an infinite time limit. Whereas here I'm deriving a very short time scale out of that. Okay, so this may not be, it may be related to some finite time Lyapunov exponent. It can be something which is, you can start from something which is not chaotic, there's inhomogeneity, all that kind of thing. But the scaling is going to be pretty much the same, log n. So and also there can be, this is purely integrable chaotic. You might have some intermediate situation, some mixed phase space kind of situation where these things may not be that clean, this kind of arguments.
In the first one also you have this omega derivative of
Yeah,
so you find that they will large.
yeah. If you make large, yeah, then it's smaller. If you make it 0 like a harmonic oscillator, it's forever there. So it's not valid in that case. Basically, this time will be infinity. Harmonic oscillator does not. So again, this is a condition which we required for KAM also to be valid. Yeah.
Here n we are thinking of a single oscillator degree of freedom like this. So n is the number of oscillator levels.
Which one? Capital N. Yeah. Yes. Good point.
But now if you have, let's say some, a chain of finite dimensional systems, then are we, so will that n go into the inverse space dimension or not?
Yeah. So good question. Yeah. So many degrees of freedom, and you have, you don't have different n though, okay? You have only one h anyway. There's only one Planck constant. So I would say that even in those cases, this is still true, but I would agree that there are interesting situations not explored, where let's say that you have some highly chaotic system which is weakly interacting with a regular integrable system. Now these are interesting situations where what is the Ehrenfest time scale and so on. You're very quickly at the border of my ignorance.
So you talk about, like, you defined earlier the Lyapunov exponent for classical trajectories as the space between the, how it like changes and when.
Yeah.
So how do I visualize this kind of a quantity for a quantum system?
You don't, because there's no phase space, you can't visualize it. However, that said, I am trying to visualize, even quantum mechanically, I'm trying to visualize what's happening to a wave packet which is spreading and so on. But yeah, I mean, it's not like the wave packets are spreading in some exponential way in this sense. People have tried to define, so there are, like for example, OTOC is one attempt at understanding that. Hopefully I will, next lecture, hopefully come to something like that. Yeah, but all of those things are, you should take all of these things critically and look at it. This is an evolving field with, arguments like this. And this is the mildest of arguments, okay, which is order of magnitude arguments.
So a mathematical formula that you will derive for the classical case of the Lyapunov exponent, does that hold for a quantum system as well?
See, the problem with those kind of things, and when you ask whether it holds for the quantum, as I said at the beginning, right, the basic object, the phase space, is a different, there is no phase space quantum mechanically. So you have to think of other ways of what is the proper correspondence. As I said, things like looking at the Liouville equation versus corresponding quantum objects. There are, or correlations, how correlations are decaying classically, quantally, and so on. Yeah, but here, just this phase space, you can see more. Okay, so let's try to move on. So let's come to, so I have been talking about time evolving states. This kind of came later in the day. The first people were looking at eigenstates and eigenvalues, because this is what we are used to doing when we are given a quantum mechanical problem. And so, and eigenstates are influenced by time evolution. That's why I also showed you first. Eigenfunctions, so let's first talk about some generalities. What are we talking about? We have some Hamiltonian. I don't know whether it's chaotic or not and so on. And this is, I'm finding out eigenvalues and eigenfunctions. What do we expect of these eigenfunctions? Now, we are used to eigenfunctions of a harmonic oscillator, for instance. We know that in 1D harmonic oscillator, I don't know how many of you have done 1D harmonic oscillator using coherent state representation. That's the simplest way in which you can look at eigenstates of a harmonic oscillator. It is just Z to the power of n, essentially, with Z being this kind of phase space point. But basically, it is maximum at the phase space orbit. Let's say this energy shell, if you look at a coherent state or Husimi representation of a harmonic oscillator, it will be peaked at where the energy, corresponding energy of the oscillator is, this energy. So corresponding to that, it will be peaking around that. Why is it peaking around that? Because that entire energy shell is an invariant object. We talked about invariant densities. This entire energy shell is invariant. It doesn't change with time, and therefore eigenstates are things which don't change in time, and therefore they will be invariant objects. They will correspond to classically invariant objects. And so what was expected when people started talking about chaos is that they will localize on classically invariant sets. But what are classically invariant sets? There are many. Periodic orbits are invariant. But periodic orbits are a set of measure 0 in a chaotic or system. And what is measure 0? Measure, remember, is volume, and there is a measure now h, which is setting the lower bound on the scale because of quantum mechanics. And therefore, the feeling was that classically invariant sets which are smaller than h cannot influence the eigenfunctions. Again, loosely, these are kind of expectations. However, there are no invariant sets. Suppose you take a fully chaotic system, for example, a double pendulum. There is nothing conserved except energy, and therefore there are no classically invariant sets of finite measure except the energy shell itself. And therefore it was argued that for chaotic systems, eigenfunctions must just, like 1D harmonic oscillators, they must be on the energy shell alone. So now the Husimi function I introduced, this Wigner function is used very extensively in this context. Another phase space representation of this defined like this. So there is this wave function psi of q, q is shifted by x, and there is this momentum p, and you integrate out over x. That gives you a function on phase space, which is a real function for any function psi, but it need not be positive, unlike Husimi function. So this has some interpretations, but it's been widely used in all of physics for a long time. And here is an hypothesis, again due to Berry and Andrei Voros, the late 80s probably, or actually probably even earlier than that, probably early 80s or 70s, late 70s, that if you take a Wigner function of a chaotic eigenfunction, it will be like a microcanonical ensemble, basically spread out over all energy shell without any structure. This is just normalization. Okay? So that's microcanonical. So this is what is the hypothesis. It's an interesting hypothesis. It looks very simple. You can do following. You can integrate out the momentum. That's the advantage with the Wigner function. If you integrate out momentum, you will get the density of modulus psi q squared. And if you integrate position, you will get the momentum intensities. So you have the probability of finding the particle at q, finding the particle at p by integrating it out. So you integrate out the momentum from this, assuming that, assuming nothing actually. No, probably you're assuming that this is of the form, standard form of kinetic energy, p squared by 2 plus v of q, then you can derive this, left as an exercise, okay? But it has an interesting structure. It says that there is nothing greater than E equals V of Q. That's like the energy is should be smaller than this potential. So this Q has to satisfy this condition. And then there is E minus V of Q to the power of D by 2 minus 1, where D is the number of degrees of freedom. So you see, if D is 1 in the 1 degree of freedom, this actually blows up at the turning points when the energy is equal to V. This is what we call turning points in a potential thing, when energy is equal to the potential energy, total energy. And we know that for a harmonic oscillator in 1D, for instance, all these eigenstates have a peak at the turning points. They look like this. But you see, when D is 2 degrees of freedom, we know is the smallest value of chaos. This is constant. That means that this intensities are constants on this energy shell. D is the number of degrees of freedom. 1 degree to, and then if your D is 3, it's even vanishing at the energy shell. Okay, so there is a interesting difference just from this. So it vanishes on classical boundaries for D greater than 2, is constant for D equal to 2. For integrable systems, this is all for expectation for chaotic, it can actually blow up at caustics. We saw things like particle in a circular cavity. There were these caustics where all the orbits were tangent to one curve. So it can blow up at these kind of points. Now there are other consequences which was derived by Berry and probably Voros at the same time. That was just the intensity at one point. You can ask for correlations, 2-point correlation in these wave functions. And you can derive these 2-point correlations between the points x and q, defined like this. You can average over some small local region But this is coming out really easily because this Vigna function itself already has the structure. So you just have to take the Fourier transform of this Vigna function here and then derive this. And you can derive that this is a Bessel function of order d by 2 minus 1. The argument is x into p divided by h bar, where x is this x, p is related to q like this. So what it means is that this correlation dies down for x which is much larger than h bar by p, which is a de Broglie wavelength. Okay, so it's a very short correlation length of these wave functions in this situation. So these were all coming from this particular Berry-Voorhees hypothesis. There's also another model which was made by Berry, which is related to this, called the random wave model, and that assumes the following. It assumes that locally wave functions, 2 degrees of freedom wave functions, for example, is a random superposition of plane waves. So locally meaning locally in momentum or energy. So let's just think billiards to be, because in billiards you have only, anyway, there's no potential in that, it's a free particle. So plane waves are natural in that, but it's not, it's bouncing around and then there's interference. By the way, this is something which I probably did not mention. One of the major differences between integrable billiard and non-integrable. Integrable billiard through any 2D billiards, through any point in the billiard table, there can be only 2 trajectories. There can be only 2 possible momenta at that point, let's say like that. Whereas in non-integrable, there can be infinity. So they can cross one point with infinite number of momenta. So you can now imagine that each of these directions, there is some plane wave going. And is a superposition of these random plane waves in which this kx and ky, the momenta, are such that kx square plus ky square is fixed, these wave numbers. And this an are random numbers, which amplitudes are random. Okay, this phase also can be taken to be random. A is the area of the billiard. And so this is a random wave model of what's happening in a chaotic eigenfunctions. And in fact, a remark is that people like Srednichi and others developed quantum statistical mechanics from such innocent assumptions. And also eigenstate thermalization hypotheses kind of started from these kind of models.
I didn't understand the correlation. So you are saying that Cxq is the correlation between wave function at 2 different space points?
Yeah, yeah, exactly.
This is correlation or the overlap of wave function?
Yeah.
What do you mean by correlation?
Precisely this. That's the overlap of wave function at points separated by x at q.
So it's an overlap, not really correlation. Or you call that correlation? Correlation of
Yeah, correlation, yeah, I mean, correlation is some overlap. So it's how the function at, how much the function at q looks like
I would say
after a distance x.
coherence of the 2 points, right? Because if 2 wave functions are, means 2 positions are uncorrelated or in terms of coherence, that will go to 0, right? Or correlations we know are like some observables, there 2-point correlations or like that. Even like when you was defining Rule polycot.
Yeah, so there it is in time, here it is in position, but yeah, so, okay, whatever you want to call it, that's the object. So what it is saying is how different is a wave function at q from x? Or how far, yeah, how are wave functions separated by x different, rather, at q, how are the wave functions at x separate?
I'm trying to think this, because you see that when we do quantum static also, in the density matrix, we drop these off-diagonal elements calling this random phase approximation.
Yeah.
Does it have any relation with this kind of quantity which you are defining here? The random phase approximation
Yeah.
drop off-diagonal elements of the density matrix.
In a way, yeah. I think probably in a way, yeah. I would say that. But I don't know whether this is directly related to a random phase approximation, but Yeah.
So Arul, so there is no connection with the Lyapunov exponent in these expressions.
No,
Uh,
they are eigenfunctions. So Lyapunov exponent is more like a time kind of quantity, which is, these are stationary states, so they should be related more to invariant objects. Already things have, yeah, that kind of
so
things.
one should be able to recover the. I believe if I have some initial state, I can decompose in terms of these
Eigenfunctions, yeah, yeah. That's a, yeah. So that's an interplay between dynamics and eigenstates, because yeah, you can get one from the other, but that involves a very different. This is looking at each eigenstate alone.
So I think I'm missing the point here. So you started with some Hamiltonian with their eigenvalues and eigenfunctions.
Yeah, we want to understand. I'll show you concrete examples. I'm just showing you kind of generalities of what people developed, what kind of models people were developing to understand these kind of eigenstates of chaotic systems.
So this hypothesis, if it was chaotic, then that functions, all of the eigenfunctions will satisfy that.
Yeah, this is one of the hypotheses. Okay, and from this, it is interesting that that simple microcanonical kind of thing leads you to all of this. This is a kind of a separate assumption, because this is telling you more about more like a global thing. This is telling you a little bit more details, as we will see.
So no dynamics happening.
There's no dynamics. Where is dynamics in eigenfunctions?
Yeah, so just based on eigenfunctions, you are trying.
This is eigenfunctions. We are looking now at eigenfunctions.
But differentiating between chaotic versus
Yeah.
normal.
Yeah. So here is this is from Arndt Barker's thesis. He's done a lot of work on billiards, especially with cardioid billiards. We've already mentioned the cardioid billiard earlier lecture. Circular billiard is integrable. Here is the classical orbit, one classical orbit, and then bunch of quantum objects. What is plotted here is modulus psi squared in position representation. Okay, so this is the excitation level, so 1000, 100 to 2000. These are the eigenstates, and you can see these various structures. They are, you can see quantum classical correspondence in these kind of things. You may think about this as an invariant object and maybe related to some object like this and so on. Okay, there are these caustics, and they will appear here. Now this is a single regular, I mean singular or a single chaotic orbit, and these are eigenstates more and more excited, and you can see that the nodal structures are becoming smaller and smaller, and they are finer and finer. 2000 excited state. It looks like it's spread all over the place. So this is this state. This is modulus of psi square. There are these patterns which are there, and in fact those patterns, this is coming from this assumption of this random waves. If you take random waves and superpose it, it looks locally almost like this. If you take the amplitudes of this thing in a plane wave representation of this billiard and plot it, so you would plot something like the distribution of AN, you'll see a very nice Gaussian distribution. So it looks like there is a lot of truth in these kind of random wave or approximation assumptions for typical eigenstates of chaotic systems. This is the distribution of the intensities. You're expanding this wave function in some basis like this, and you are finding out what are those coefficients. And so, I mean, you would, for example, expand this in some basis, right? You would diagonalize it in some basis, so that amplitudes have a distribution which is a normal distribution. Yeah. This is just the amplitude of this state here. Okay, we'll come to that. We'll come to such things in more detail,
So
but
Arul, from that pictures which you are showing,
yeah.
you are saying large excited states mimic classical behavior, or is that
Not necessarily. We don't know what is the, no.
What is
I'm,
information you were
nothing. I'm saying that how do random states, how do chaotic states look? Excited states so far, what I have said is they look like random waves, superpositions. That's all I've said. They look like random waves.
But the classical one was the red one, right?
This is classical orbit, but you can't say that this is like this or anything like that. Okay.
No, because the orbit looks more like that than other.
No, the orbit, by the way, if you just integrate infinite time, which you should, this is not an invariant density, it will just fill uniformly. Yeah. These are not uniform. These are actually, there are fluctuations.
So then why are you showing those things even for integrable and non-integrable both cases?
I'm just showing the kind of differences which are there in an integrable and non-integrable case. The 2000th excited state for a circle, 2000th excited state for a cardioid billiard. Okay, now is that the whole story? So this is what was thought till about the early 80s. So this is like the stadium billiard. People thought that most of the eigenfunctions were like this, delocalized all over this thing and maybe in some random superpositions of waves. They recognized that there were kind of different kind of states here. You can see the state which is highly influenced by in this vertical direction, which has classical orbits just bouncing between these straight lines. That's clear that that's a periodic orbit. And therefore, this is one of the orbits which will show up in quantum mechanics also. But that's actually a continuous family of neutral stable orbits. They are showing up in this wave function. But it was realized about by Eric Heller, who did some of these computations in the mid-80s, that there were highly excited states which showed actually quite remarkable concentration and not just as random waves. There was this state, for example, which is showing this concentration of intensity along this direction, which is also the direction of an unstable periodic orbit. You can imagine an orbit just bouncing between these things. It's unstable. This was not expected to be there in periodic orbits or a set of measure zero, but nevertheless, they were showing up in single eigenstates. And then he found many examples of this, so things like a bow tie, and these are periodic orbits, which are unstable periodic orbits around these. So these are from some early papers of ours. I mentioned the quartic oscillator. So these that was also chaotic, and you can see that these are 4 eigenstates with pretty 1376, 1377 with different. So you can see how different they are. They're just next to each other in energy. This is again modulus of psi x y squared all over the place. This symmetry is coming from the symmetry of the wave function, but this can be along this periodic orbit. It is highly localized. And this is in the case where it's unstable. It can be stable also sometimes, and it will show up in these extraordinary situations. So these were called localization on sets of measure zero, which are these unstable periodic orbits, were called quantum scars by Heller. And so one of the important things is that the orbit has to be unstable for it to be qualified as a scar. If it was not unstable but stable orbit, it's more or less WKB quantization. So that is not to be considered, strictly speaking, as a quantum scar. There are theories developed for quantum scars, mathematical theories about their origin and so on. But all the time evolution which I showed you at the beginning, they are all related to this in the sense that you can take let's say a fixed point at the origin, and because the time evolution does not move it away, even in the unstable case for some time, it is sufficient for a eigenfunction to be stabilized at that point, or to show that. It's not as if that's the only feature in that. So a typical eigenstate, even which is scarred, will have some random background to it, as well as these kind of classical structures. I should probably just be winding down. So I'll show you the eigenfunctions for the standard map, which we have been looking. We'll look at Husini functions of these. Okay, so we can now diagonalize a finite n dimension and we will look at how the eigenfunctions are looking in phase space. Can I just take 5 minutes? I'll finish with this. So n is 100, k is 0.5, remember, is not chaotic. It's there are these km tori, and there are 100 eigenfunctions I've managed to squeeze into this. Each one is a coherent state representation. You can see that this is influenced by the periodic orbit at the origin. This is by the period 2 orbit, but we would not call this cars because they are actually stable orbits. Here you can see the island around this, it's forming around this. So, yeah.
They are at different energies, right? All
They have different eigenvalues. So actually here, because it's a Floquet system, we call this quasi-energy. So this phi j plays the role of the energy. They're all having different energies. Different quasi-energies, exactly. And you can see these structures here, they're all like, these ones are km tori. So they are influencing this. So you can see that most of it is km tori, or they are influenced by these fixed points or period 2 orbits. Stable, here this is influenced by the unstable fixed point. You still won't call this scarring, although this is unstable orbit, because it's not really chaotic, it's not in this thing. But it's coming close to being scarred. So there is this range of eigenfunctions. If we increase k more, you have more chaos which is forming, but you can still see that a lot of eigenstates are influenced by these regular orbits, and most of it is influenced by regular orbits, but maybe this one is having some amount of chaos in that, maybe starting to develop. And k equal to 2, there's a substantial amount of chaos which is developing. So there are many eigenstates which are like this. There are some which are influenced by the periodic orbit at the origin, which is stable, and the associated stable orbits in that island. But many of them are becoming more and more spread out in this phase space. They may also be getting scarred. We don't know. Like for instance here, you're seeing like 6. This could be a scarring by a period 6 orbit. This is for 4. You can see that this orbit at the origin has just become unstable. It's still, there are these island structures around it. Eigenfunctions are being localized around it. And, but most of the eigenstates are now starting to get delocalized in phase space. 5, there are still, now if you find anything which is at the origin, then it's likely to be scarred, but such states are not really, there is classical islands around that. So it's being influenced by that. So actually scars are this is for the Baker's map where we know all the periodic orbits. So it's more easier to identify. There's no parameter, but you can see that this is clearly a period 4, this is a period 2, 1/3, 2/3, 2/3, 1/3. And there are associated other orbits, not just periodic orbits, some homoclinic orbits and so on, period 2 orbit scarring. So there is a lot of scars which are going on in this n equals 64 for the Baker's map. The difference between k equal to 7 and n equals 64 Baker's map is that Baker's map Lyapunov exponent is small, is log 2. Whereas this one can be large, the standard map Lyapunov exponent can be large, and so there can be more scarring in this weak chaos, if you wish. Okay, so as we are increasing n, this is for n equals 128, it's a power of 2, and you get many eigenfunctions. Somebody mentioned multifractals. Actually, many of these eigenfunctions are multifractals when n is a power of 2. They are related, I mentioned in probably my second seminar on the Tuemor sequence. We found actually that some of the eigenfunctions where n is a power of 2 is a beautiful influenced beautifully by these kind of Tuemor sequences. So you can get almost an analytic approximation to many of the eigenfunctions of this highly chaotic system. Okay, so I think I'll stop with that. We'll go into details of the structure of these eigenfunctions, more about the randomness, how to quantify them, how to measure their randomness, and then I'll go into eigenvalues. I'm not sure that I'll go into much of many-body at this stage, but okay, I still have 7 slides in this only, so maybe at least a glimpse of that. So I think I should stop. Thank you very much.
So, any questions?
People are tired.
So I guess you were saying quantum scar in your those
Yeah.
quantum eigenstate. Is those chaotic, means in the chaotic region, those state which match with the classical orbits, those are
Periodic orbits.
sorry, classical periodic.
Yeah, they can be influenced by other orbits
But
also,
also
but
actually
essentially
unstable
periodic,
also,
unstable, because they're all chaotic. If they are not unstable,
Yeah.
you would not call that. So there is a whole lot of many-body literature, literature on many-body scars. Most of the literature is not clear what it is underlying, whether there's any unstable structure which is underlying that. It's a different phenomenon maybe. We'll come to that.
Also in the anybody starts in any places is not so much.
Yeah. So there are theorems in quantum unique ergodicity theorems which apply to ergodic quantizations or ergodic systems which don't seem to agree with scars. So there is mathematically it's kind of it's acknowledged that there will be a set of measure 0, and as you're going up in energy it will become rarer and rarer, the scarring. But nevertheless, there's a lot of experiments which have observed scarring, not just in many body, but in chaotic systems. And so they are very much real, and they do influence, interesting influences they are.
All that lead to weak chaos, you just mentioned.
Huh?
Weak chaos. You said
I said weak chaos in the sense of the Baker's map, where the Lyapunov exponent is not very large. So then you might be able to see some of these things more. So it's still chaotic, but not super chaotic, or in some sense the Lyapunov exponent is positive but not very large.
But my question was appearance of scar.
Yeah.
Does it also control chaotic behavior or not important?
Does it control chaotic behavior?
Yeah.
In a sense that if you start, and this is how actually they find many body scars and all that, but when I started showing things like I'm starting from a fixed point, that fixed point can be unstable, let's say in a chaotic situation, K is 7. By the way, I mention these things because I'm hoping that these experiments can be done very easily. You don't have to integrate even a billiard and so on. You can do these experiments in half an hour or 1 hour. So you take that orbit and then you evolve it for some time. And then take a Fourier transform of that, so that the wave functions, eigenfunctions, will be influenced by this kind of time evolving state. So, if you start from a scar, a periodic orbit which can scar, and if it remains in that region of the scarring region for some time, it is allowing a wave function, eigenfunctions, to be built on that object. But of course, that's not the only thing, because there will be a diffusion later on and it will go away, so there will be other structures, random structures. So the cat map which I mentioned and the quantization of that, in that cat map, it has been shown that that the weight of in an eigenfunction, the maximum weight that a scar can have is 1/2. So you have other structure.
In this many body community, they say the scar like also leads to oscillation in physical systems.
That's because they are starting from that scarred state, or if you start from the scarred state, nothing, it's an eigenstate or something, but around that object, let's say that something is scarred by, yeah. So that is similar to this, right? I mean, if you start from a periodic orbit.
So I'm saying then that controls chaos, right? Because if it leads to oscillation rather than harmonization or mixing.
Yeah.
So no, I'm saying if
Yeah.
you start with
It kind of is let's say that in a sea of chaos, it is some low instability regions. Okay. I'm sure that it won't be there forever. There will be some time scale at which it is there and it is disappearing. But it depends on the system. And there are some, yeah.
So you said that in a classical chaotic system, the unstable periodic orbits are dense. Does that have any analog in the quantum scarred eigenstates? being selected in the quantum eigenstates, or how do I?
Actually, that's a hard question. I'm sure that any answer that I give is not going to be very correct uh, because the influence of periodic orbits in these eigenfunctions is mostly of low period. There is some limit on that. Okay, so we can also recognize only low period scarring because of this interference which is happening. So that's why you need more, yeah, I mean, I can't answer some question like that very definitively. And also all the theories about scarring, most of them, all of them actually, there's only a few which is using semi-classical theory. They are not to do with single eigenfunctions, but to do with some averaging or some energy window, and then to see whether scars come out from that. So yeah, I think it's still debated a lot even in the semi-classical chaos community. The presence of scars and whether it is there, it can be an emotional issue for some.
That's what you said, also good point, because in many body systems, many of them, they don't have even semi-classical analog.
They don't have, yeah.
So how your definition will go there?
Right, they understand that at some early point, and then people were telling them where is the instability. So they changed their definition and they said that wherever states have some low entanglement or something, they'll call it scarred. Basically, wherever, so you have a bunch of states which are looking very chaotic or random. In between that, at the same energies, you are having a state which is behaving very differently, in some sense localized and so on.
These things, I don't know how good that one, recently, that this scarred state will be written more in a product form in terms of the localism or local.
Maybe, yeah. So again, yeah, so maybe more like matrix products or something, yeah. It's possible because again, they are low entanglement states, so likely to be having some representation like that. Yeah, but in the absence of a classical limit, I think you need some other definition of scars, but people have just taken it up as a jargon. Yeah.
In classical context, we have like in cat map, like it's a recurrence after some time, and also in quantum map.
Only in the cat map, huh?
Only in the cat map.
Only in the cat map.
And quantum map, can we have an analog of like pointer recurrence in quantum map?
Yeah, okay, very good. Yeah, thanks. Yeah, there is certainly, there's work also done on that kind of thing. One thing I did not mention, and what he's mentioning is the Poincare recurrence theorem, which says that, okay, you can have chaos, you can have whatever, well, he wasn't even talking about chaos. Any Hamiltonian system, in fact, any measure preserving system, any orbit comes arbitrarily close to itself, arbitrarily many times. So that's a Poincare recurrence theorem. It comes arbitrarily close to itself. It's not like it's going to some other, that is ergodicity. This is saying that it's coming to itself. So this is not, it looks like then there is periodicity, but this time is very large. And that's the Poincare recurrence theorem. There are versions of these for the quantum case as well, but again, these are very large. They are like exponentially large in this n, which would be the system size. Yeah, and those are certainly very long time scales to see recurrences. But yes, there are equivalent of these, of the theorem as well as that. But actually, I haven't seen any practical, the cat map is a very special case. Yeah.
Okay. Is there any other question?
I don't know whether in the YouTube there's anything.
Anything on YouTube? Is there any question?
Yeah. Not as far as I know, but that doesn't mean much. You have to find out. I don't know. Actually, I should also say, since you're asking, that there is a fair bit of applications of these things and semi-classics in this situation to very practical problems like waves in the ocean. So oceanographers, actually, I have a colleague in IIT Madras, ocean engineering, who's doing things related to these random waves and superpositions, as well as, yeah, things like these. So I don't know whether scars are important there. Could be.
Any other question?
But could you say only quantum one scar, right?
Yeah,
But then the ocean, why is the quantum?
waves. I mean, so the equivalent of the waves, and then the wave equation there is looking like Schrodinger equation. Yeah. So, and also, yeah, you can have waves in, okay, one whole series of analog experiments deals with microwave cavities. Those are really classical, right? There one has found a lot of these phenomena. So there you can say is also classical waves, perhaps. Yeah, yeah. Absolutely. You should have I know that this institute, Raman, has tabla, so you should have a tabla with a stadium billiard and play around with it. In fact, yeah, there are interesting things like that. Yeah.
Okay, so let's thank Professor Arul one more time.
Thank you.
Side teams, enjoy.
And you will come soon, okay, 5:30. Okay, I will see you.
All right, bye.